Cemal Yılmaz, right? I'm a professor of computer science. My research interests include software engineering in general and software quality assurance in particular. That is to say that anything that can help us produce better, faster, cheaper, more reliable software systems is on my radar. Right, having said that, here is the deal. Well, throughout this talk, in this talk, I will assume that we have software-based digital art, in the sense that, you know, in the creation of the digital art of interest involves the development of a piece of software system. Okay, so throughout this, I will assume that. So we are doing programming, we are developing a piece of software for the creation of this artwork, right? So this is interesting because if you really think about that, even in Turkey, we teach programming at middle schools, even at primary schools. That sort of suggests that it is inevitable that we will see more and more of software-based digital art in the future. Therefore, we should really start discussing how to take care of that digital art, right? So here we go. So as you can see, I'm a newcomer to this field, and I must say that I have so far read only a limited number of papers in this field. But one thing that I realize is that, you know, many of these works basically talk about preservation-related activities as activities that need to be carried out right after the artwork has been created. And in this talk, my ultimate goal is to convince you that this is something, like the preservation concern is something that should be addressed right from the beginning, right from the first day of the art project. Why? Here is why. Because it is similar to something that because it is similar to some of the very serious mistakes that we as software engineers used to do, right? For example, when it comes to software quality assurance, we as software engineers used to think that, well, it is something that we should do right after we have developed the software system, right? And it unfortunately took us years, and it took us thousands, tens of thousands of failed software projects to realize that that is not the case. We should really take care of take the software quality assurance activities into the account right from the first day of our software project. And I believe that preservation is not any different. It's no different than that, right? In the sense that preservation the concern regarding the preservation activities should be an integral part of the life cycle of any software-based digital art project, right? So that is what I will do. So that's what we should do during development, right? We call it development, during the development of this artwork or the creation of this artwork. So another question is, what should we do after the artwork is created? Well, there I strongly believe that we should regularly keep our software-based digital artwork up to date with the evolving technology, and we should do this regularly. So it means that we should, in a sense, since I'm assuming that software is involved here, in a sense, we should regularly update the software to cope with the changes in the technology, right? So why is that the case? Here's why we should do that. Because if we don't do this, in the sense that if we wait until the end, then the more we wait, the more technical debt will be accumulated. And the more accumulated technical debt, the more it will be difficult for us to preserve the artwork. Well, in this context, in the context of software engineering, technical debt is a concept reflecting the implied costs of additional rework caused by choosing an easy solution. So that means that every time you choose an easy solution, you are accumulating technical debt. And if you don't take care of that technical debt, at some point, it will basically go, right? It will basically go into the junk, and you have to restart everything. You have to start developing everything from scratch. Okay, so that's why I strongly believe that we should take care of this before we arrive at the age of disappearance of the artwork, and we should regularly update that. Another interesting thing is that there seems to be a lot of issues in this context that are familiar to us as software engineers, right? Many of those issues we as software engineers face in our standard, in our regular software engineering projects. And therefore, I strongly believe that we in this field can inherit many of the well-established software engineering principles, guidelines, tools, frameworks, approaches, techniques from the field of software engineering. As a matter of fact, what I'm going to do is that I'm going to briefly go over all those things that we can inherit from the field of software engineering very briefly. I'm going to discuss those things very briefly. And then interestingly enough, we have some problems. We have some really interesting and challenging problems, domain-specific problems specific to this domain, which can attract attention of the software engineering research community. And I'm going to also go over some of those problems and try to briefly explain them for you. All right, let's continue. So here is the thing that don't be alarmed with this picture. So here's the thing what I want to do. I want to, in order to understand the source of the problem, I guess we need to first understand what is going on inside our computers, right? So I'm gonna briefly, very briefly, don't be alarmed, very briefly talk about the hardware and software stacks in problem, just to be able to, help you understand what the real problem is. So this is hardware. Here we go. All programming languages are compiled into machine instructions, and then they are executed. Those instructions are executed. Well, the hardware component, which is responsible for executing those machine instructions, is called CPU, which stands for Central Processing Unit. Those instructions, as well as the data that they manipulate, stored in memory. Well, this memory is called RAM, and in short, it stands for Random Access Memory. And the CPU and the RAM communicates with this thing called bus. Right? You can consider bus as a wire connecting the CPU to the RAM and the RAM to the CPU. And then we have all these I/O devices like keyboard, monitor, printers, hard disk connecting to the same bus so that they can communicate with the CPU and the RAM. Right? And everything is printed on a digital circuit which is called motherboard. So this is the hardware part, right? So hardware stays right here. So let's take a look at the software stack now. Well, in the past, when we were developing programs, software systems, we were developing them right on top of the hardware. That means that in the past, we were supposed to write our own device drivers for the CPU, our own device drivers for the keyboard, for the monitor and everything. And we had to do that for every system, every software system that we develop. And we have to do that from scratch. Then we said that why are we doing this every time from scratch, every time when we need to develop a piece of software? Why can't we hide the dirty details of hardware from programs running on top of the hardware? And we said, that's a good idea. Then we created an abstraction layer around that hardware. That abstraction makes the hardware transparent to the software, so that today when we are writing programs or developing programs, we don't really care about, unless otherwise needed, we don't really care about what type of keyboard is connected to the computer, what type of display is connected to the computer, because all those dirty details are hidden from us because of the operating system. Well, on top of the operating system layer, we have the application support layer, the goal of which is to hide the dirty details of the operating system from the programs. So it makes the operating system this time transparent to our programs. And on top of the application support layer, we have the applications, and our digital works will be in that layer, right? Digital works will be in this layer, and then we'll have like web browser, office software, and so on, right on top of the application support layer, right? Okay, let's take a look at the complexities of today's systems. Hardware, we have billions of transistors. Software, we have tens of millions of lines of code. Even we have billions of lines of code, like the code base maintained by Google. So, can you imagine how difficult to produce a piece of software? It looks like an insane task, right, to produce a piece of software, because we have billions of transistors interacting with hundreds of millions of lines of code, and still we as software engineers can develop software systems that do whatever we want them to do. It's like, an insane task, right? So here we go. How do we deal with this complexity? Well, it's simple. We use two mechanisms. One is the divide and conquer mechanism. This is very powerful because as software engineers or computer scientists, here's what we do. We divide a problem into sub-problems. We divide sub-problems into sub-sub-problems. Sub-sub-problems into sub-sub-sub-problems until the problem is easy enough to be addressed, to be solved by a single developer. So when every developer works on a simple problem, like a piece of the problem, then what we do is that we put those pieces together. And it is something like building, it is something similar to building with Lego blocks, right? We have individual Lego pieces, we put those individual pieces together to create larger structures, we put larger structures together to create even larger structures, and we keep going on until we get what we want to get, right? And when we are doing this, we use abstraction. And that's to say that when we are putting these individual pieces together, we don't, as software engineers, we don't really care about the complexities involved in the development of these pieces. We don't really need to understand how those pieces are actually implemented. All we care about whether those pieces can be put together or not, right? And in order to put them together, their interfaces should match. So it is similar to building something with Lego blocks, because here is the deal. In order to put two Lego blocks together, well, their interfaces should match, in the sense that, well, in this particular context, you can consider the interface of a Lego block as the number and orientation of those bounds on the surface of a block, right? As long as they match, you can put these two Lego blocks together. It is the same thing, the same story. As long as the syntax and the semantics of two software-based pieces match, we can put them together to create a larger structure, to solve a larger problem. Okay? Well, so far so good, right? Then what is the problem? Here comes the problem. Our artwork lives on top of this hardware and software stack. However, our artwork will have no control over this stack. Our artwork will have no control over these layers. And unfortunately, those layers may change, their interfaces may change, their implementations may change, the way they interact with each other may change, they may even become obsolete. And when these changes cannot be accommodated, cannot be addressed, our digital artwork may disappear. And believe me, this is not a question of if, but when. Because there are many studies strongly suggesting that the biological half-life of software-related technologies is about 5 years. That means that any software-related technology that you use today in your digital artwork is likely to extinct within a decade or so, within a 10 years or so. Okay, so what we need to do is that we need to address all these changes in a timely manner to ensure a long lifespan for our artwork. So what I want to do is that now I want to go over some of the very simple techniques, the principles and guidelines that we as software engineers apply to our projects, right? So here is the first one. The first design principle, it says that anticipate obsolescence. This is a pretty well-known software design principle, which basically states that plan for changes in hardware and software platforms. So here you see some guidelines. Let's go over that very quickly and try to understand what they mean. Avoid using early releases of technology. Right? Why? Because early releases of a technology tends to have many defects, and in the presence of a defect, what we typically do is to implement a workaround. However, when those defects are fixed in the subsequent version of the technology, our workarounds may conflict with those fixes, and then this may create an issue for us. Another guideline: avoid using undocumented or little used features or software libraries. So here we go. Here is the deal. So when things go south in software engineering projects, when, for example, the resources are scarce, software developers will ask these questions to themselves. Well, I don't have enough resources. I cannot support all the features I've been supporting so far. What if I stop supporting this feature? And to answer such questions, they will carry out an analysis which we call an impact analysis. They will ask themselves this: what if I start? What will be the percentage of my end users that could be affected by that change if I stop supporting this feature? Well, if it is a little used feature, then the answer is very easy for the developers. Well, it's a little used features, I don't care about that, I'll stop supporting that feature from this point on. Well, if you end up using that feature in your artwork, you'll be in trouble. Another one: avoid using software hardware from companies that are less likely to provide long-term support. It is a bit harsh way of saying that do not buy technologies from small companies because it's harsh, I know that, but that's what it means. So because if they are here today, but they may not be tomorrow. And when if they run out of business, then who's going to provide you with technical support? Another one: use standard languages and technologies that are supported by multiple vendors. That is a way of saying that do not use proprietary technologies, because if you do, you will be stuck with a single vendor, and that's not good, right? Instead of using proprietary software systems, you may use open standardized systems, standardized technologies, or open standards, because in such case you will have multiple vendors. If you are not happy with a single vendor, or that single vendor, one of these vendors goes out of business, then you will have all these other vendors line up for you, right? So these are, simple principles. Oh, by the way, I forgot to tell you this, but I understand that the artists may not be able to obey these rules because they are artists. They have to be creative and so on. But I also understand that artists typically work with programmers or software engineers, and at least software engineers or those programmers can apply these principles. So here is also a related design principle. It says that design for portability. This is very important when it comes to preserving digital art, because this principle states that design your software system such that it can run on as many hardware and software platforms as possible. And one way to ensure that is to use cross-platform programming languages. So here is an example. Java is a very well-known, frequently used cross-platform programming language. Here is the deal with these languages, right? But regular programs are compiled into machine-specific instructions, and they are executed then by the CPU. Java, as a cross-platform programming language, is compiled into machine-agnostic instructions, which are often referred to as bytecodes. Then those instructions are fed to a virtual machine called Java Virtual Machine. And the Java Virtual Machine is responsible for converting those machine-agnostic instructions to machine-specific instructions so that they can be executed by the underlying CPU. That means that as long as you have a Java virtual machine implemented on a platform, developed for a platform, you can run your Java code on that platform. As a matter of fact, I don't have that. In the smart cards, we actually run Java virtual machines. Right? So, oops. Believe it or not, here, we are running Java virtual machines. Right? That means that we can run our programs in here. Well, I'm exaggerating because the type of Java programs that you can run here is actually a small and safe subset of the full-fledged Java programming language. But still, the idea is same. As long as you obey them, you can run them here. Okay. So here we go. So this is good. But another thing is that even if you are using like the cross-platform programming languages, you need to be really careful about not using any platform-specific libraries. As a matter of fact, if you want to create like a portable software systems, you need to use standardized interfaces as much as possible. So, for example, we have standardized interfaces for operating systems, we have standardized interfaces for programming languages, as well as for parallelization. So going back to operating systems, we have this thing called Portable Operating System Interface, in short, POSIX, which was standardized by IEEE. What happens is that if you only use this interface, this POSIX interface, to communicate with the operating system, then it means that you can easily port your system from one operating system to another operating system, supporting the same standard without any hassle. So the same also is true for the programming languages. For example, for C programming language, we have standardized interfaces like ANSI-C and ISO-C. Well, if you use those standardized versions of the C programming language, then it is guaranteed that your C programs will be compiled by all the C compilers out there which support this standard. And it is also guaranteed that the semantics of your programs will be preserved across platforms, across hardware and software platforms. So it is very crucial if you want to create portable software systems, and I strongly believe that creating portable digital which can work on many platforms as possible, will significantly increase the chances of preservation. And these are important things. Well, here we assume that we know the dependencies, but remember that we are sitting on top of the hardware and software stack, and we don't really know what is going on in these underlying layers, right? Therefore, we are not necessarily aware of the dependencies that we create in our implementations. When we are doing programming, when we are coding, like developing a digital art, we don't necessarily know the technologies that we depend on, right? Because of all those layers of technologies. We don't know what is going on in those layers, right? Fortunately, we can use static and dynamic program analysis techniques, approaches, which can automatically determine all the technologies, all the software libraries, all the software packages that our implementation depends on. And such a report, like you can automatically create a report, your system depends on this version of this library, that version of that package, this technology, and so on. Such a report can then be used for risk assessment. As a matter of fact, we have software metrics measuring or quantifying the level of portability that a software system has. For example, we have software metrics quantifying the direct portability of software systems, quantifying the installability of a piece of software, replaceability, adaptability, and so on. So we have all these software metrics, and I strongly believe that we can inherit those metrics from the software engineering field. And one interesting research question is that can we generate domain-specific software metrics, like like the preservability metrics for software-based digital art? Well, that's another thing, because like if you can come up with Well, I'm just speculating. If we can come up with a, well, this we can. Next, whatever I will say next, I'm speculating. If we come up with a preservability matrix for software-based digital art, which will quantify the level of preservability the digital art has, then what can happen is that instead of doing that manual work, trying to figure out what the dependencies are, the museums can go ahead and in the blink of an eye quantify the preservability. And in the blink of an eye, then they can do whatever they want to do. They can, for example, I don't know, for the regions where the preservability is poor, I don't know, they can ask the artist or the programmer, well, let's make it more preservable. They can suggest techniques to the artist or the developers working with the artist to make it. They can even come up with like standards for accepting or buying digital arts. I don't know, that part is a speculation. Right. Oh, by the way, the terms here, software engineering terms here, are given in orangish color. If you are interested, you can go, look them up later on, right? All right. So these are dependencies, right? Well, as software engineers, we don't like dependencies. So here is the deal when it comes to dependencies. As software engineers, when we see a dependency, the first thing that we ask is, can I get rid of that dependency? If we can, because sometimes accidentally you create dependencies. If you can, get rid of that dependency. If you cannot, the goal is to reduce the strength of that dependency. And at a very high level, here is how it is done. To reduce the strength of the dependency, rather than creating direct dependencies, we create indirect dependencies. And one way of doing that is to use software design patterns. Well, at a very high level, here's what they mean. It turns out that we have some recurring problems in software engineering. That is to say that we have some problems that are frequently faced in different contexts, in different projects and so on. But they're the same problem, right? So, well, in the past we were doing this. Every time we face a problem, like a recurring problem, we were solving it from scratch. Then we said that, why are we doing this? Right? So then we said, why don't we figure out all these recurring problems and then provide efficient and effective solutions for each problem and document those solutions so that others, when they see the same or similar problems in their project, can adapt our solutions. Right? Those solutions are referred to software design patterns. Right? These are pre-formulated solutions for frequently appearing problems. And using software design patterns, right, is a way of learning from the experience of others, which is quite important when it comes to software engineering. In a facade module. And this facade module will actually play the role of an abstraction layer, hiding all the details, dirty details about these packages from the rest of the system. Only this module will be visible to the rest of the system, and the rest of the system will not be aware of the fact that these packages are already there. So here is the deal. So if these packages become absolute, or if these packages change, right, and you really need to accommodate the change, then hopefully all you need to do is to update your facade. And that update, all those changes, hopefully will be transparent to the rest of the system, because the rest of the system will not even know that these packages exist. Right? So here is, like I said, rather than creating direct dependencies, create indirect dependencies through an abstraction layer. Okay? Okay, well, we talk about dependencies. Okay, we know what dependencies we have. We reduce the strength of these dependencies, but it may still be quite difficult and quite expensive for us to put all those dependencies together. Right? In such cases, the best bet we have is to use virtualization technologies. as a matter of fact, overall, I believe that this is one of the best bets that we have to preserve digital art, right? What is virtualization? So here's the definition. Virtualization is a process of running a virtual instance of a computer system in a layer abstracted from the actual hardware. So basically, just to help you visualize what it is, by using virtualization technologies, you can run multiple operating systems simultaneously on a single machine. So here is a Mac OS operating system. In one window, I am running Windows XP or Windows 7. In another window, I am running Windows 10. Yet in another window, I am running a Linux version, like a Linux variant. So right here, simultaneously, I am running 4 operating systems. 4 different operating systems. 1, 2, 3, 4, the host operating system. Well, when it comes to virtualization, it seems that we have 2 options to use. The first option is to use virtual machines, and basically a virtual machine is an emulated equivalent of a computer system. So you can consider each of these running in a virtual machine. Right? If this option is chosen, then it means that shipping an art, I don't know the word for that, sorry, shipping a digital art, you will ship your digital art, you will publish your digital art in a virtual machine, in which all the dependencies are pre-installed. So you will create a virtual machine, you will install all the required technologies, all the dependencies, all the libraries, all the packages that your artwork requires, together with the artwork itself, package it as a virtual machine and publish that. Give it to a museum. Then the thing is that that virtual machine can be executed on any hardware, on any software hardware platform supporting the virtualization technology used. Then you can take it, run it on a Linux version, you can take it, run it on Arduino box or Raspberry Pi box, whatever. So this is the first approach. The second approach, an alternative approach, is to use virtual containers. Well, I don't want to go into the details of the differences between virtual machines and virtual containers, but at a very high level, here is what it means. A virtual container is like a lightweight version of a virtual machine, right? Well, the idea will be the same. You'll be publishing your artwork in a container, in a virtual container, where all the dependencies are pre-installed. Okay? One good thing about these virtual containers is that you can programmatically create them. You don't need to understand the code here, but here is what we are doing. I'm creating a virtual, in a sense, let me call it virtual machine. It is easier to understand rather than saying a virtual container. I'm creating a virtual machine where I install this Linux variant, this version of that Linux variant, then I create a user in that operating system, then I automatically install all these software packages, and finally I install Google Chrome. This is just a script, this is an executable script. When you execute this, the environment will be created for you in the blink of an eye. Right? Boom, 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 everything needed will be downloaded from internet, and the virtual environment in which you're going to run your digital art will be created. Right? This is as simple as that. Okay, we talked about the dependencies, we talked about the environment, but obviously to ensure, you guys don't like this, but to ensure preservability, we need the source code of the artwork, not the source code of our dependencies. We need the source code of our digital artwork. And I'm not just talking about the final snapshot of the source code, I am talking about the history of all the changes made to the code base. Right? So, in order to keep track of the history of the changes, history of the code base, one technology that we can use is software repositories, right? We can use software repositories such as Git or SVN to do that. Right? And in this repositories, the versions and the releases of our software should be clearly tagged so that we can deterministically reproduce the code base. For example, we use in 2016 in the Metropolitan Museum of Art of New York, and we can then deterministically reproduce the other version of the same code base which we use in 2019 in Istanbul. Right? If we have these code repositories around, we can deterministically reproduce the code, and this is very, very, very important. It is not just about preserving or keeping track of the source code. We should also keep all the test cases around. So Patricia talked about it, right? Either accidentally you can create a change. You may cause a change in the behavior of the artwork, right? You never want to do that. So you take this, right? When you're installing it at a museum, after the installation, you want to make sure that everything is expected and that you did not change the artwork, right? Well, one way of ensuring that is to run the test cases against the artwork, right? Those test cases will verify and validate the behavior of the program, behavior of the software system, in this case, behavior of the artwork for you. Therefore, keeping the test cases, developing and keeping the test cases around is quite important. And from this perspective, we should exercise every relevant type of testing, like unit testing, interaction testing, system-wide testing, performance testing, and so on. Okay? And this is also important, all those test cases must be automated. And they must come with their own test oracle so that we can determine whether the test executions were successful or not. Right? So this test case should be push of a button thing. We should push after modifying, for example, after installing at the museum, or after performing some modifications to keep the artwork up to date with evolving technologies. We will run these test cases to see whether everything is expected or not. Well, speaking of test cases, this brings us to another pretty well-known software engineering principle, which basically states that design for testing and debugging. This principle basically states that you should take every step to make testing and debugging easier. So this principle basically states that you should design your system such that testing and debugging can be automated as much as possible. When it comes to design for testing, one thing that we can use is test-driven development. Well, in short, TDD. In test-driven development, what we do is that we come up with we develop the test cases first, even before we develop the software system. Right? Even before we start implementing the system. And for various technical reasons, this will help you come up with a software design, with a software implementation where testing can be automated as much as possible. And when it comes to design for debugging, one thing that we really need to do is to come up with highly cohesive, loosely coupled systems. Well, in particular, it means that we need to reduce the strength of the dependencies as much as possible. Okay, interestingly enough, when it comes to debugging, what is debugging? Debugging is the process of identifying and fixing bugs. When it comes to debugging, in this context, we can use really specialized debuggers. We don't need to use, on top of the regular debuggers that we have, we can use specialized debuggers. One such specialized debugging approach is called relative debugging. Well, in software engineering, we use relative debugging, especially when we are porting applications from one operating system to another operating system. So here is, at a very high level, here's how they work. You have this version of your artwork working correctly on Windows. Now you need to port it because that version of the Windows is gone. So that version, Windows XP, this version is, I don't know, Windows 10. Right? So this version, you know that this version works, this version fails. You're doing porting, this version fails. Well, in relative debugging, what we do is this. We run these two versions in parallel. We freeze the executions at certain points and compare the internal states of the program, of these two programs, to quickly pinpoint the root causes of the failure so that we can fix them. And well, therefore, as you can see, relative debugging can play a very important role in preserving digital art. As a matter of fact, I strongly believe that domain-specific debugging approaches can also be developed in this context. Documentation. We talked about the documentation. Documentation is quite important because when verse comes to verse, the only thing that we can do is to develop the system from scratch, given its documentation. Right? That's the worst case scenario. Given enough documentation, we can hopefully, develop the digital art, recreate the digital art from scratch, right? By rewriting the programs and so on. Well, when it comes to documentation, we need to take a look at the software development processes. Well, here we see two software development processes at the extreme ends of the spectrum. On this end, we have the waterfall model. This is a plan-driven, documentation-heavy development process. Well, this process basically assumes that all the documentations must be developed before we can even start implementing the system. So we have to prepare the requirement specification documents, we have to prepare the design documents, and everything must be prepared first so that we can go ahead and implement the system. Well, unfortunately, this model does not support, it simply assumes that those requirements do not change during the development. However, in practice, the requirements typically, the things that the software system is supposed to do, typically change over time during development. And for such cases, here is the other development process at the other end of the spectrum. And this is called agile development, right? Such as Scrum. So agile assumes that the requirements will change. So the agile process will tell, what is the point of writing them down? They will change soon. Right? There is no point of writing them down. So what you should care about, when those change, you should go fix the program. So here is the two extreme approaches. When the requirements change, the question for the developer is this. Should I go ahead and update the documentation, or should I go ahead and fix my program? This model will tell, I don't know what to do. The requirement should not supposed to change. So I don't know what to do. You're on your own. This guy will tell you that, are you kidding me? Forget about updating the documentation. Fix the program, because it is what it matters. It is the thing that matters. Right? So here we have heavy documentation, there we have very little documentation or no documentation at all. Well, I suspect that agile development processes are a better fit for developing digital art. But unfortunately, there we will not have any documentation, or little documentation. So here is the thing. It is said that in agile processes, the source code itself is the documentation, and that's another reason why we need the source code. So here the source code itself is the documentation. Okay? Therefore, in these processes, development processes, the source code should be kept as simple as possible. How do we achieve this? Well, here are some mechanisms. Refactoring. In agile processes, we frequently refactor the code. Refactoring is this. Refactoring is modifying an existing code base in order to make that code base more maintainable without changing the functionalities of the code base. So for a system, before and after refactoring, there will be no visible change from outside the system. But from inside the system, the system will become more maintainable. Another thing that can be used to cope with the lack of documentation is pair programming. That's also a frequently used strategy, right? We use technique to deal with the lack of documentation. In pair programming, two programmers, two software engineers sit together at the same workstation and do programming. One of them is coding, the other one is observing. They are talking with each other. Here, what should I do? What should we do now? Here, I am doing this loop. I'm creating this loop to do this and that. And they also discuss about possible corner cases and so on. So the good thing about pair programming is that it makes the knowledge of the code base shared by two developers, so that if one developer leaves, you will have this other developer which will have the knowledge of the source code. That's another way of dealing with the lack of documentation, right? Okay, we talk about documentation in natural language. Well, we can also talk about like executable specifications. Not just documentations, specifications written in natural language, but we can also have specifications that are executable. Right? As the name indicates, executable specifications are like executable statements in the source code, the sole purpose of which is to validate the behavior of the program. So that when we make a change, we make sure that what we did will not actually change the behavior of the program. Well, executable specifications can be written in the form of assertions. So here's one example. Let's assume that you have this code, right? This is pseudocode, not given in any programming language. Let's assume that we have this code which is supposed to move this ball across the screen, right? So it takes as input the distance that the ball should travel, as well as the time that it should take for the ball to travel this distance. Then what it does is that it computes the speed of the ball and do whatever necessary to move that ball across the screen, right? So here is one executable specification in the format of assertion. It says that, well, at this point, time should not be 0. Why? Because I'm going to compute the speed by computing distance over time. When time is 0, the program will crash because division by 0 is undefined. So here we go, assertion, to make sure that at this point of the execution, time is not 0. Why is this important? Because that assertion basically implies the assumption of this code base. Right? By taking a look at this assertion, you can immediately tell that, well, okay, this code assumes that time should be different than 0. Which is important, right? Because it will help, this is a documentation, right? It will help you understand what the code does. Another point is that you can turn on these assertions, you can turn on and off these assertions at will. So for example, you install something at the museum, or you change the software system for the purpose of preservation, and you now want to verify your changes, you turn on all the assertions and run the artwork. If one of those assertions fails, that means that you made a mistake. Go find which assertion failed and fix it. Another form of assertions, another better way of specifying executable statements or executable specifications is to use design by contract idea. So that's another approach that we frequently use in software engineering. So here is the idea behind design by contract. In this approach, when we ship a piece of code, we ship it with a contract. It's a two-way contract. On one way, that contract specifies what the user of this code should expect from the code. On the other hand, it specifies what the code is expecting from the user. These are executable statements, specifications. So here we go, going back to our running example, moving the ball across the screen. So here is a contract. Take a look at this statement. It says it requires time should not be 0. So this is what the code expects from the user. Take a look at this ensure statement. It basically says that, well, if this condition is satisfied, I guarantee you that I will move this ball at a constant speed where the speed is computed like this. And here is an invariant which states that I will guarantee you that through the movement, the shape of the ball will not change. Right? This is like precondition. If that precondition is satisfied, I'll guarantee you that. And when I'm doing that, this will always be true. These are executable. You install the art. You install the art at the museum. You change the software system for preservation. You turn on this contract. You say execute the contract, and if the contract is breached, you'll get notified right away, so that you will know where you have the failure, which part of the system failed. Well, obviously, these are like somebody has to write them, right? Which can be error-prone, which can be difficult, which can be tedious. But fortunately, we have dynamic programming analysis approaches, which can automatically discover the contract for you. Right? So, for example, given this ball moving across the screen, these approaches, by analyzing the data collected both from inside the executions and outside the execution, these approaches can infer the fact that the ball moves at a constant speed, can automatically infer the distance traveled by the ball, the time that it took for the ball to travel that distance, together with the fact that the ball is a circle and the shape of that ball does not change throughout the movement. All those things can be automatically discovered. So this contract can be automatically written, so that when it is time to change, we can run this automatically discovered contract against the modified version of the artwork to see whether everything is expected or not. We talked about preserving the digital art, but unfortunately it looks like it is not just about preserving the art itself, we should also preserve the environment that the art leaves. So here's an example. So let's say that I have a digital art and it requires some web pages or web servers. The art is running in Istanbul, it requires a web server in Japan, or a web page in Japan, right? So in this case, it is not just about preserving the art. We should preserve that web page or web service also. However, we don't even have the binaries for those services, right? They are geographically located at a different geographic location, right? So the thing is that, I can preserve the art here, but without preserving that web service, it will not have any meaning, right? I should preserve the web service too. However, I cannot do that because that web service is like running in a server and I have no control over that server. I cannot simply copy the web service because I don't know the source code, I don't have the binaries. One thing in such cases that we can use is to mock the environment. That's what we call mocking. Well, in this case, what we can do is that we can create a mock environment. Well, in this context, a mock object replaces an original object. And it does nothing but simulates the original object by replaying previously recorded interactions. So from outside, a mock object will look like as if it was a real object, but it is not a real object. What it does is that it simply replays pre-recorded results for us. So here is how mocking can work here. So we have this web service, right? So here we go. This is our digital art. We're going to create a control layer around the digital art. We run the digital art. The digital art will communicate with the environment like that web service. Right? We capture all the interaction between the digital art and the environment and store all these interactions. Like for every request coming out of this digital art, we're going to intercept it, record the request, we're going to forward the request to the web service will reply, we will intercept the reply, record the result. and forward the result back to the digital art. This is the capture phase. In the replay phase, here's what we're going to do. We're going to run our digital bird. Our digital bird will think that it is communicating with the environment, while indeed it is communicating with our control layer. There will be no service here. The environment is this. We capture the environment. So here will be our mock environment, simply replaying the pre-recorded interactions for that digital art. Okay? Well, here's a concluding remark. Like I said before, preservation concern is something that should be an integral part of the life cycle of any software-based digital art. And after the art has been created, it should be maintained regularly. And waiting until the age of disappearance of the artwork in this context will be too little, too expensive, and too late. Well, that's my 2 cents, and I know that this is pretty technical, but I hope you got.
Thank you.